Let's take a look at what's meant by zeros of a quadratic polynomial and the relationship between zeros and coefficients. So, a real number k is said to be the zero of a polynomial p of x if p of k is equal to 0. Now, what do we mean by that? Let's take an example. If I say that x minus 4 equal to 0. If I take the value of x is equal to 4, then 4 minus 4 is equal to 0. That means 4 is the 0 of the polynomial x minus 4. That is, when I substitute the value of x with 4, then the polynomial resolves to 0. Let's take another example. Let's say x square minus 5x plus 6. What happens if I take the value of x is equal to 2? So this becomes 2 square minus 5 into 2 plus 6, that is 4 minus 10 plus 6, which is equal to 0. So the value of x is equal to 2 gives the value of the polynomial as 0. Therefore, 2 is a 0 of the polynomial. What happens if I take the value of x is equal to 3? Then I get 3 square minus 5 into 3 plus 6, which is 9 minus 15 plus 6, which is also equal to 0. So x is equal to 3 is also a 0 of the polynomial. So both 2 and 3 are values which are considered as zeros of this quadratic polynomial. Now, there is a relationship between the zeros and the coefficients of a polynomial. What are coefficients? They are the constants attached with the variables. Now, any standard quadratic equation can be written as ax square plus bx plus c equal to 0. So my quadratic polynomial is ax square plus bx plus c. What are my coefficients in this polynomial? Well, my three coefficients are a, b and c. Now, suppose alpha and beta are the zeros of this particular polynomial. That means if I take the value of x as alpha or if I take the value of x as beta, then substituting x with alpha or beta will give ax square plus bx plus c is equal to 0. So x is equal to alpha or x is equal to beta. These are the two zeros of the polynomial. Then in that case, x minus alpha and x minus beta are the two solutions, the two roots for this equation. Now, remember, if alpha and beta are the zeros, then the sum of the roots, which is alpha plus beta, is given by minus b by a. So the negative value of the coefficient of the x term divided by the coefficient of the x square term will give you the sum of the two roots, and the product of the two zeros, alpha into beta, is given by c upon a. So the constant term divided by the coefficient of the x square term will be equal to the product of the two zeros for this polynomial. Very interesting property. Let's take a few examples to understand how exactly this works. So we have our first question. I have to find the zeros of the quadratic polynomial x square minus 2x minus 8 and verify the relationship between the zeros and the coefficient. Now, to find the zeros, I'm going to split the middle term. Remember, I have to split the middle term such that when I multiply the numbers, I get 8 and the addition of the terms is minus 2. So I can write this as x square minus 4x plus 2x minus 8. Minus 4x plus 2x is minus 2x. Minus 4 into 2 is minus 8. So from the first two terms, if I take x common, I'm left with x minus 4. From the next two terms, if I take plus 2 common, again I'm left with x minus 4. So taking the x minus 4 is common, I get x minus 4 into x plus 2. So x is either equal to 4 or x is equal to minus 2. Right? So my two zeros are 4 and minus 2. Now, the sum of the zeros is 4 plus minus 2, which is equal to 2. The product of the two zeros is 4 into minus 2, which is equal to negative 8. Now, let us try and compare this with the coefficients. If I compare my given polynomial with ax square plus bx plus c, then a is equal to 1, b is equal to minus 2 and c is equal to minus 8. Minus b upon a is minus of minus 2 upon 1, which is equal to 2. C upon a is minus 8 divided by 1, which is minus 8. And as you can see, the sum of the zeros is negative b by a, same value. The product of the zeros minus 8, which is c by a, the same value. And hence we have also proven that the relationship between the zeros and the coefficients is sum is minus b by a, product is c by a. Let's take yet another example. This time 4s square minus 4s plus 1. So in this case, let's split the middle term as 4s square minus 2s minus 2s plus 1. So 2s into 2s minus 1 minus 1 into 2s minus 1. So 2s minus 1 and 2s minus 1. So when 2s minus 1 is equal to 0, 2s is equal to 1, s is equal to 1 upon 2. So 2 times. So 1 upon 2 and 1 upon 2. My two zeros are 1 upon 2 and 1 upon 2. The sum is 1 upon 2 plus 1 upon 2, which is equal to 1. The product is 1 upon 2 multiplied by 1 upon 2, which is 1 upon 4. Let's compare it with the standard form ax square plus bx plus c is equal to 0. So I get a is equal to 4, b is equal to minus 4, c is equal to 1. Minus b upon a is minus of minus 4 upon 4, which is 1, and c upon a is 1 upon 4. So sum of the zeros is minus b upon a, product of the zeros is c upon a, hence proven. Let's take yet another example where I have cx square minus 3 minus 7x. I need to keep it in the form ax square plus bx plus c. So rearranging the terms, 6x square minus 7x minus 3. Now 6 and 3, I can split it as 9 and 2. So 6x square minus 9x plus 2x minus 3. Taking 3x common, 2x minus 3 plus 1 into 2x minus 3. So I can take 2x minus 3 common, 3x plus 1 remaining. If 2x minus 3 is equal to 0, then x is equal to 3 upon 2. If 3x plus 1 equals to 0, then x is equal to minus 1 upon 3. So sum of the roots is 3 upon 2 plus minus 1 upon 3, which is 9 minus 2 upon 6, that is 7 upon 6, and product of the roots is 3 upon 2 into negative 1 upon 3, which is equal to negative 1 upon 2. Now, comparing the values, a is 6, b is minus 7, c is minus 3. So minus b upon a is negative 7 by 6, which is 7 upon 6, and c upon a is negative 3 by 6, which is negative 1 upon 2. So sum is equal to minus b by a, product minus 1 upon 2, hence proven. 4u square plus 8u. Now, this I can take out 4u as common and write it as u plus 2. So either u is equal to 0 or u is equal to minus 2. So sum of the zeros is 0 plus minus 2, which is minus 2. Product of the zeros is 0 into minus 2, which is a big fat 0. Now comparing it with ax square plus bx plus c, I get a is 4, b is 8 and c is 0. So minus b upon a is minus 8 upon 4, which is minus 2, and c upon a is 0 upon 4, which is 0. Again, sum of the zeros is minus b upon a, product of the zeros is equal to 0. So proven. Now t square minus 15. Now this is a pretty interesting example. T square minus 15 means t square is equal to 15. So t is either positive root 15 or negative root 15. So sum of the roots is positive root 15 plus negative root 15, which is 0, and product of the roots is root 15 multiplied by negative root 15, which is minus 15. Comparing it with ax square plus bx plus c, we get a is equal to 1, b is equal to 0, c is minus 15. So now minus b upon a is 0 upon 1, 0, and c upon a is minus 15 upon 1, which is minus 15. Again, sum of the zeros minus b by a, product of the zeros c upon a. So in every case, we are able to prove the relationship between the zeros of the given polynomial and the coefficients. Let's take an example, 3x square minus x minus 4. So I can write it as 3x square minus plus 3x minus 4x minus 4. So 3x into x plus 1 minus 4 into x plus 1. Taking x plus 1 common, I get 3x minus 4. So x plus 1 is equal to 0, means x is equal to negative 1. 3x minus 4 is equal to 0, means x is equal to 4 upon 3. So sum of the zeros is minus 1 plus 4 upon 3, which is 1 upon 3, and product is minus 1 into 4 upon 3, which is negative 4 upon 3. Now comparing it with ax square plus bx plus c, a is equal to 3, b is equal to negative 1, c is equal to negative 4. So minus b upon a is minus of minus 1 upon 3, which is 1 upon 3, and c upon a is minus 4 upon 3. So again I get sum is minus b by a, product is equal to c by a. So as you can see, it's very easy to solve these problems, but you need to practice how to split the middle term so that you can easily identify the zeros of a given quadratic polynomial. After that, it's easy to remember sum of these zeros is equal to the negative value of the coefficient of x divided by the coefficient of x square, and the product of the zeros is equal to the constant term divided by the coefficient of the x square term.